This is Academic Chemistry 4.2, Part 4. So in this video, we're going to talk about Ernest Rutherford and his gold foil experiment. This is actually my favorite experiment, partially because I worked with a Mr. Rutherford, not to be confused, two totally different people, and he also taught chemistry with me. But it's also just a really clever experiment. So we're going to see how this experiment goes against the plum pudding model we saw from J.J. Thomson before. All right, so Ernest Rutherford and the gold foil experiment. So this all started in 1909, so just over 100 years ago, like really not that long ago. Rutherford started shooting alpha particles at substances to see how they behave. So the first thing we need to discuss is what the heck is an alpha particle? So this is the image of what we can imagine an alpha particle looks like. So alpha particles are two protons and two neutrons. So since protons are positive, neutrons have no charge, then the only charge in this is positive. Also, keep in mind, out of subatomic particles, which are really small, alpha particles have four large subatomic particles, so they are fairly big. Basically, this is a helium nucleus and no electrons in it. So it's positive, it's bigger than most subatomic particles. It's also part of radioactivity, so this is something that a radioactive substance might release, and it's part of radioactive decay. So if you ever are talking about something being radioactive, alpha particles might be being released from that substance. So keep in mind at this point, scientists didn't know what a neutron was. They didn't fully know what an alpha particle was made of. They didn't get that yet, but they knew it was large for really small things and it was positive. So those are the two key things to remember about the alpha particle. So large compared to other subatomic particles because it has four grouped together, and positive charge because protons, it has two protons, those are positive. Neutrons have no charge, so the overall charge of this alpha particle is this positive one proton, positive one proton. Overall, this thing has a positive 2 charge. These neutrons have no charge, no electric charge to them. All right, so this is the setup for Rutherford's experiment. So he has this radioactive source. So this source down here is shooting out alpha particles. And he has this bit of gold foil. Now, what you don't see in this picture is this gold foil is incredibly thin. It's just a couple atoms thin. So it's literally the alpha particles that are being shot out. This red line represents the alpha particles. They're just hitting a little bit of gold foil. And now this is a plate that can actually detect where the alpha particles hit, so you can see it. You can't really see alpha particles in real life. You can't see radioactivity. So we need something, this is probably coated with phosphorus, so you can actually, when the alpha particles hit, you see, boom, the alpha particle hit there. All right, so this is what they thought the atom looked like. Here's Thomson's plum pudding model in its finest. So Rutherford expected alpha particles to pass straight through the gold foil because they thought, okay, the atom's mostly empty space, and you have these teeny tiny little particles just randomly throughout them. I mean, look at this alpha particle. It's way bigger than any of these things. So if these are just one little subatomic particle, even if the alpha particle hits one particle, which you don't see in this path, but let's say, it does this and boom, hits that a little bit. Well, since the alpha particle is bigger than any of these subatomic particles inside the atom, then you would expect those subatomic particles to kind of just like scooch over and the alpha particle just shoots straight through. Like that's what you think is going to happen. But it didn't always happen that way. Most of the time, it went straight through. But once in a while, you had this deflection where the alpha particle hit and then went back here. Or sometimes you might have one of these or one of these. It was so shocking to Rutherford. It would be like if you took a gun and shot it at a tissue paper and the bullet came back and hit you. Like he was astonished. So because the particles were sometimes deflected by the gold foil, the plum pudding model couldn't be correct because it didn't work out the way they expected. So because these alpha particles were sometimes deflected, that means there must be some part of the atom, some dense positive center that would deflect alpha particles. Remember, it has to be dense because it has to have enough mass so when the alpha particle hits it, it deflects it. It also has to be positive because if that dense area was negative, if the alpha particle that's positive hit it, it would just stick to it. So it needs to not only be able to deflect it with a lot of mass, but it also needs to have the same charge as an alpha particle, so it also gets deflected. It also has to be super, super small because most of the time the alpha particles still went straight through. So most of the atom, the alpha particles goes through, and then boom, once in a very blue moon, meaning it's a very small, small, small area. So this makes a lot more sense for the atom because if the particle goes here, passes straight through. But if it goes here, it's going to be deflected. So you know that these positive things have to be in the center. So Rutherford called this dense positive center of the atom the nucleus. So we're getting a lot closer to what we think of as the modern atomic structure. And that's it for Rutherford's gold foil experiment. And I will see you in the next video when we talk about how we figured out about neutrons.